Hey, what is up everybody? It is Mr. Boylan. And today, what in the heck are we gonna do in this video? We're going to explain the law of conservation of energy, define heat, and perform calculations involving heat, mass, temperature change, and specific heat. So basically, pretty much what we've been doing this entire unit. However, we're gonna break it down a little bit differently this time. First, going to explain how the average kinetic energy of a substance relates to the phase of that substance. 2, we are going to label and explain parts of a heating or cooling curve. 3, numero 3, we are going to define and calculate molar heat of fusion or molar heat of vaporization. And then number 4, we are going to calculate total heat absorbed or released during a phase change. Okay, so first things first. Up until this point, we've really been focused on the heat that's been absorbed or released during a chemical change, chemical reaction. But you should recognize that in addition to chemical reactions, heat is also required when it comes to phase changes. So we're now going to be talking about how much heat energy must be absorbed or released to transition from one state of matter to another. So basically, as you take a look at this thriller of an animation from the University of Colorado, you need to think about adding heat to a solid. Boom! Or adding heat to a liquid, or to a gas, or removing heat, cooling things down. What does that mean for the state of matter? How can we transition from one state to the next? Solid, liquid, gas, 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 liquid, solid. Add, remove heat. Now, as you take a look at your notes, you're provided with some of the different phase changes that you have to be familiar with and some of the specific names that you need to be familiar with as you're working through this unit. Now, most of these you're probably pretty familiar with if you have, I don't know, lived. However, we're going to start using things like fusion or vaporization or maybe even solidification. So be confident that you can understand what those terms mean in terms of what phase we're starting with and what phase we're transitioning to. Okay, now a great way to sort of observe the amount of heat added in order to get a substance to change from one phase to the next is to look at a graph that is called a heating curve. And this graph just shows you the temperature of the system versus the amount of heat added. Now here is a fantastic heating curve that I really like because it shows you at the top the particulate view of the phase of matter that you're dealing with. But this is what we're talking about when we're talking about a heating curve. Now, there are going to be some important calculations that you need to be able to do based on that heating or cooling curve. First, you need to be able to calculate the energy change of the sloping segments. Slope, using the formula Q equals MC delta T, which at this point you should know and love very much. Some things to think about as you work through the calculations of those sloping segments of a heating curve. Recognize that the angle of the sloping portion is related to the specific heat of the phase of that substance. In other words, the steeper that slope is, the lower the specific heat. In other words, the less energy you have to add to get 1 gram of that substance to increase 1 degree Celsius. The more gentle the slope, the higher the specific heat, the more energy you have to add to get 1 gram of that substance to increase 1 degree Celsius. Now, on the plateau segments, plateau, you are simply going to multiply the number of moles of your substance by what's called its molar heat of fusion or its molar heat of vaporization. Now, these formulas are not provided to you on your formula chart, so you will have to recall that you simply need to multiply number of moles N by either the enthalpy of fusion or heat of fusion or the heat of vaporization, just depending on what it is you're working with. Now, it's important to notice that when you solve for the heat along the plateaus, there's no delta T, there's no change in temperature because during a phase change, the substance remains at a constant temperature. It's also important to recognize that that heat of fusion or heat of vaporization value is unique to each particular substance and is usually measured in kilojoules per mole or joules per gram. The length of that plateau is directly related to the amount of heat required to make the phase change. Okay, so let's take a quick look at a fantastic heating curve for water. that you have in your notes. It's really important that you take some time to look at this heating curve and examine the different segments. And when it comes to calculating the heat absorbed along this heating curve, are you working on a sloping section? Boom. Or are you working on a plateau section? Boom. And as you take a closer look at segment 1, because it is a sloping section of our heating curve, we are going to use the Q equals mc delta T equation to solve for the amount of heat required in order to get 1 mole of ice at negative 25 degrees Celsius up to the melting point of 0 degrees Celsius. Some important quick notes: recognize that we've taken our 1 mole of ice and converted it to mass in grams, so about 18 grams. And then also notice that we use 2.09 joules per gram degrees Celsius, which is the specific heat of solid water or ice. Okay, next we're gonna take a quick peek at segment 2. It's a plateau region. And notice in this region we have both solid and liquid water. Now, as we take a look at the heat required to overcome all of those intermolecular attractions and melt all of the solid and transition to the liquid phase, notice at this time, in order to calculate the heat required to do that, we're simply going to use the number of moles of ice and multiply it by its molar heat of fusion. In this case, for water, it's 6.02 kilojoules per mole. We just multiply 1 by 6.02 kilojoules per mole, which gets us to 6.02 kilojoules. So a word of caution here as you think about doing a calculation for a sloping segment versus a plateau segment. Take a moment to look at the formulas we use, and also take a moment to recognize the units. Many times when we solve for Q using Q equals mc delta T, our initial unit is in joules. However, when we're using molar enthalpies of fusion or vaporization, it's going to end up often in kilojoules. So just be cautious to make sure that you translate your units to the same unit at the end. And then to think about how much heat is required to get this 1 mole of solid water at negative 25 degrees Celsius to 1 mole of water vapor at 125 degrees Celsius, you simply need to add together all of the heat energy for the individual segments of your graph. Again, take a couple moments to study that on your own. Heating curves and calculations using heating curves are going to be important for this unit. Okay, and then the last 2 things to keep in mind when we think about heating curves, keep in mind that because temperature is a measure of average kinetic energy, any change in temperature is a change in kinetic energy. All of the sloping line segments on a heating or cooling curve show a temperature change and therefore a change in kinetic energy. During these regions, a single state of matter exists and the sample is either getting hotter or cooler. It's important that along these sloping segments you recognize that there is going to be an increase in average kinetic energy as we get that single phase either hotter or colder. And lastly, recognize that during the plateau line segments there is no change in temperature, so kinetic energy remains constant. Remember, temperature is a measure of the average kinetic energy. The 2 phases are in equilibrium, so we've got this dynamic back and forth between the 2 phases. All of the energy that is absorbed is related to changes in potential energy. In other words, breaking the intermolecular forces of attraction between the molecules. So for the plateau line segments, remember the 3 P's. Plateau, phase change, potential energy change. Plateau, plateau. Again, notice we've got 2 phases in equilibrium. The temperature remains constant. All the added heat goes to overcome the forces of attraction that are in between the particles. Okay, and that does it for this video. Always take a quick moment to check out some of the links to where I pulled some of those great animations and video simulations from.